Today, I'm taking you on a surprisingly dramatic journey into the world of Coronaviridea, the viral family in 2020 that decided to redecorate our entire planet. This is my deep dive into SARS-CoV-2, what it is, how it works, why it spreads so quickly, and how it compares to its spicy feline cousin. SARS-CoV-2 is a member of the Coronaviridea family, a group of crown-wearing RNA viruses named for their spike proteins. Before 2020, most human coronaviruses caused mild colds, quietly minding their own business. This one decided to say, however, I'm built different, and launched the biggest microbiology lesson of our lifetime. Today, let's break down its anatomy and its replication. This virus belongs to the beta coronavirus genus, alongside SARS-CoV from 2003, MERS-CoV, and several bat coronaviruses. One especially interesting relative is the feline coronavirus, which usually causes mild digestive problems in cats, but sometimes it mutates into feline infectious peritonitis, or FIP, a severe inflammatory disease driven by infection of immune cells, a much severe disease. So, same family, different hosts, different types of drama. Let's talk architecture. SARS-CoV-2 is roughly spherical and 80 to 120 nanometers. The major components include spike proteins, which bind to the ACE2 receptor, membrane and envelope proteins, which help organize the structure, and nucleocapsid proteins, which wraps around the RNA genome like a protective blanket. The spike protein is the real star of the show. It's responsible for attachment and entry. Membrane proteins help shape new viral particles, and envelope proteins assist in assembly and release. Because the genome is positive sense single stranded RNA, it can start making proteins immediately as soon as it enters a host cell. There's no warm up needed, it just takes over. Since we know viruses can't grow and reproduce by themselves, SARS-CoV-2 must hijack the host cells. It binds to the ACE2, fuses with the cell membrane, and releases its RNA into the cytoplasm. It basically takes over and says, hey, I work here now, and then uses its host ribosomes to build viral proteins. Replication happens in a few key steps. First, attachment to the ACE2. Next, fusion and RNA release. Then we have translation of viral proteins. Next, DNA replication by viral polymerase. Then we have assembly in the endoplasmic reticulum and the Golgi apparatus. And last, we have exocytosis, where new viruses get shipped out into the body like millions of tiny little Amazon packages. Now let's talk about what happens when the virus enters the human body and how our immune system responds. On the left, you can see the model of the virus that I made. Those red spikes are what our immune system focuses on first. When the virus enters, our innate immune system jumps in immediately. Things like macrophages, dendritic cells, and interferons try to slow it down. Think of it kind of like bouncers at a club trying to keep the chaos to a minimum. But the real power comes from our adaptive immune system. B cells start producing antibodies that specifically recognize those spike proteins. Meanwhile, T cells hunt down the infected cells and destroy them. This tag team response is what clears the infection. And then, better yet, it creates memory cells so your body remembers the virus in the future. Vaccines take this system and helps give it a head start. The COVID-19 mRNA vaccine basically delivered the recipe for the spike protein only, but not the whole virus. Your cells make harmless copies of the spike, your immune system sees it, and your body builds those same long lasting memory B and T cells. So when the real virus shows up, your immune system is already ready. Variants show up when the virus makes small mistake, so mutations, while it's copying its mRNA. Most mutations don't matter, but some change the shape of the spike protein just enough so that it affects how the antibodies recognize it. That's why we had variants like Delta or Omicron, and that spread more easily and it escaped partial immunity. The virus wasn't becoming a new species, it was just kind of shopping out parts and upgrading its attachment tools. But overall, the body between the immune system and variants is a constant race. The virus mutates and the immune system adapts, and vaccines help us stay ahead of this by several steps. Feline coronavirus, however, spreads mostly through fecal oral route, specifically in multi-cat environments. SARS-CoV-2 spreads through respiratory droplets and aerosols. What they do share is its adaptability. Small mutations can dramatically change disease severity. Feline coronavirus mutates into FIP, which is a perfect example of how the virus can shift gears. SARS-CoV-2 spreads efficiently because people can transmit it before systems even appear. Aerosols makes it easy for the virus to hang out in the air, especially indoors. SARS-CoV-2 has a simple structure, but it's incredibly efficient. Think small genome plus rapid mutation plus high transmission equals global pandemic. Comparing it to the feline coronavirus, it shows how host species shape disease outcomes. Understanding the Coronaviridea family helps us predict future outbreaks in both humans and animals. Thank you for watching. Hopefully, this gave you a clear and engaging look at the SARS-CoV-2's world, as well as the viral family it comes from. This tiny virus changed our healthcare system, our lives, but studying it helps us prepare for whatever nature decides to throw at us next.